Going to work through problem 4.48 from Taylor's Classical Mechanics, chapter 4. This is a problem involving an inelastic collision, a perfectly inelastic collision. So it's giving us that a particle of mass 1 and speed v1 collides with a second particle of mass 2, which is at rest. The collision is perfectly inelastic, meaning that the particles lock together. So this is what happens. They lock together and travel off at some velocity. We want to know what fraction of kinetic energy is lost in the collision. So we want to know our initial minus our final over our initial. That'll give us the fraction lost in the collision. So how much, this is the amount lost, how much of the original kinetic energy does that make up? What percentage? And we want to comment on the cases that M1 is less than, much less than mass 2, and also the case that mass 2 is much less than mass 1. So this is what the question is asking us. I'm going to start by using the momentum. We know that the momentum will be conserved. So our momentum is going to be our M1 V1 is equal to M1 plus M2 V prime. This being our final velocity when they lock together, their masses add. We can solve that for V prime. So now we get that V prime is M1 V1 over M1 plus M2. We know our initial kinetic energy is going to be 1/2 M1 V1 squared. We know our final kinetic energy is going to be 1/2 M1 plus M2, that final mass, V prime squared. Using this, we know that our kinetic energy, our final kinetic energy is going to be 1/2 M1 plus M2. Substituting in this expression for V prime and squaring it, we end up with M1 squared V1 squared over M1 plus M2 quantity squared. This is going to take care of that square. So our final kinetic energy is going to be 1/2 M1 squared V1 squared over M1 plus M2. Now, we want to take our initial, subtract our final, and divide by the initial. That'll give us our fraction. We have everything we need now. We just need to carry out this operation. So dividing by that initial can be expressed as this. 1/2 M1 V1 squared. 1 over that times this whole operation. The initial, 1/2 M1 V1 squared minus our final, 1/2 M1 squared V1 squared over M1 plus M2. When this divides out, we're just going to get 1 multiplying out into our brackets. That's going to turn into 1. We're going to subtract that 1/2, going to go away, divide out. M1 is going to take 1 off the square, V1 squared go away. And 1 minus M1 over M1 plus M2 equals our TI minus TF over TI. So the fractional change in kinetic energy, how much is lost? Okay, so we can put this all into one fraction. You have M1 multiplying by the denominator to get a common denominator, M1 plus M2 minus M1 over M1 plus M2. Now we can simplify this out. We're just going to have M2 over M1 plus M2 equals our initial kinetic energy minus our final kinetic energy over the initial. This is the loss as a fraction of the initial. So this is exactly the expression we need. Now they're asking us, okay, what if M1 is much less than mass 2? Also, what if mass 2 is much less than mass 1? You can see if mass 1 is much less than mass 2, this denominator will barely change, and this expression will approximately equal 1, which as a fraction is almost 100% of kinetic energy is lost. It's like throwing a rock at the earth or a rock at the sun. A small rock that you can throw compared to the mass of the earth or sun, all of that kinetic energy is going to be lost. Now, when mass 2 is much less than mass 1, so you're throwing a bigger object at a smaller object, almost none of the kinetic energy is lost. You can see this is going to be a very small numerator. That's not really going to have an impact on the denominator. Large denominator, small numerator, small percentage, almost no kinetic energy is lost if you are throwing a big object at a small one, by mass, of course. So we've answered the question, and I hope that gives you a better understanding.